Okay, sounds good. So this week is when I get out my electricity and magnetism book and I sort of hopelessly page through all like 600 pages of it. Not really. So what we're going to talk about today is the Maxwell equations in the static case. So in the case when the charges or the magnetic fields aren't changing very rapidly. So what are we talking about actually, sort of experimentally? How do people actually figure these things out? When I was in London for about 10 years, and so I went to the museum where they have the actual laboratory of Faraday, where he was working out some of the rules of magnetic fields, the direction of magnetic fields, and currents, and Faraday wasn't big on math, so he was really just trying to sort of like work out with just simple wires and magnets. You know, what are the rules for how these magnetic fields work? And so, actually, most of what we're going to talk about dates back to that that time, because we're not going to worry about electromagnetic waves that can propagate through the vacuum. So the thing that I mentioned last time, so we have the electric field, which is some kind of invisible field that is caused when you have a charge, and then the magnetic field, which is a different thing. There are no magnetic charges, and so magnetic fields only occur when charges move, or alternatively, you sort of like move a wire through a magnetic field, or change a magnetic field past a wire. So those fields are actually they can't be anything. So part of what the Maxwell equations are about is kind of specifying what shape in space can these fields have. And so if we start off with our normally there's 4 Maxwell equations. We'll just have 3 because we've kind of combined them into the statics case. So the first one is pretty familiar, looks like what we had before, which was that if you take the divergence, which means sort of the radiatingness of a scalar field, of a vector field, but that vector field is the conductivity times the gradient of the potential. So the gradient of the potential is just a scalar, just a number, sort of like you can think of it as the voltage at a point. So this gradient turns that thing into a vector, and then we multiply it by a number, the conductivity, and then we take the divergence of it, and that finds out how radiating this vector field defined by this is, and that equals basically the current. It equals the divergence of the current. So the current vector is the one that we're going to want to try to figure out. Where is the current flowing in the cortex? So that's basically these are our sources. And this is some of the data, some recordings, the data recordings. So that's one equation. It just says if you do it looks pretty much like the one that we did for the current source density, except that you've got the conductivity in it. So the second Maxwell equation doesn't really have a name. This one is this one is let me just give me a little more space to write under it. So remember, So this is div, and that turns, vect to num. So how radiating or contracting is something. So this is the conductivity, how easy it is to get charges through something. This is the potential. This guy is grad, that steepest uphill direction. This guy is another div, and these guys are currents. So the next Maxwell equation specifies a very particular thing about what kind of magnetic fields can you have. And so this one says that the divergence of the magnetic field always has to be 0. And whenever I see these equations, I go like, as I was watching my video from last year, it's like 0, that doesn't help me. So what does that mean? So what this means is that if you look at the magnetic field has a very particular structure to it, and it can never be radiating. It always has to be circulating. So you can never have magnetic field vectors coming out from a point. So another way of saying that is there are no magnetic charges. Because if you have a charge, the electric field, depending on the sign of it, the electric field will point either out from a point or into a point. That's a charge, like a positive or a negative charge. But there are no magnetic charges. So there's no magnetic charges where there's just a little point and then the magnetic field points into it. Instead, what this equation says is that the magnetic field always has to only have circulating, sort of circular type, rotating components to it. It can never have this radiating component. So that would be true for the electric field if you had no charges. So if you were just out in absolute outer space and there's no charges, complete vacuum, then this would be true for the electric field also. But as soon as you have any charges, then you're going to have these radiating. The vectors will sort of be radiating or contracting. Okay, so then the last one is what was called originally Ampere's law. So this one is basically describes how the magnetic field relates to currents. So this guy says that the rotatingness, the curl of the magnetic field, is equal to that constant that has to do with how well the magnetic field goes into a particular substance. And then it includes two things. It includes the currents, but then also maybe there's some charges in there. And so we have to sort of add on to that the gradient of the potential. So this guy was called the permeability. I mean, how easy it is for magnetic fields to get into the substance. And this guy's the conductivity again. And these are, our impressed currents. This is our data again. I mean our sources. So this is, sources. So we also have the B here now. So if we're doing MEG, this potentially could be the data, because the MEG detectors will measure the magnetic field. So that's the Maxwell equations in the static case where stuff isn't moving around very rapidly. So you look at that, it's kind of, they're sort of like constraints. They don't really kind of help you somehow. So what we want to do is sort of back up a little bit just to the very simplest case of the potential just for a charge. So say we just have like just a single charge out in space. So, and what we're going to work up to is the forward solution, how to calculate basically what the voltage at a point is and what the magnetic field vector at a point is. That's the given some source. So that's what the meaning of that. Let's just write that down. So forward. So you'll see this a lot, sort of forward solution. In many different fields, there's like a forward solution and an inverse solution. So the forward solution means, for some sources, somewhere in the brain, calculate the potential and the magnetic field vector at point somewhere else. That's my technical definition of the forward solution. Okay, so you've got some sources somewhere in the brain, little current dipoles, and we'll talk about a dipole. We'll start off with a single source, and then what you want to do is calculate like what's the potential over here at this scalp electrode, and what is the magnetic field vector at that scalp position. So that's the goal. So we'll start off with the simplest case, which is just the potential for single charge. So potential for one charge. So that gives us a simpler equation. So the equation for the potential for a single charge is basically it's just 1 over the distance. So that between where you're measuring it from and where the charge is. So the top thing is the strength, and if it's just a single charge like an electron, then that just has a fixed strength because all electrons have the same charge, but that's the strength of the charge. And then it's over 4 pi times the conductivity, because you're in some kind of medium, and then you have the distance. So that's just the distance to the charge. So it's basically just inverse, not inverse square. So this is the strength, and this guy is distance to measure. So that's a very simple thing. So what does that look like if we? So this is something that describes our potential or voltage at each point. It doesn't really describe it at each point. It just describes it for a pair of points, like where the charge is and where you're measuring. But what if we plot it out for a whole bunch of points? What does it look like? Well, it looks like, if you plot basically 1 over r, because you can say these things are all constants. So basically this boils down to 1 over r if you're plotting it in MATLAB. So what does that look like if you just look at it in 1D? Well, it's going to be something that sort of goes up like this, and then it goes up to infinity at 0. So this is r going this way. So why is it infinity at 0? Well, as the distance goes tiny, 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 this number just gets huger and huger, and it will be infinity right at the actual location of the charge. So if we draw that out, so in reality it's in 3D, but we could just draw it out in 2D. So if we have a plus charge here, if we draw out the potential, so this direction was the potential, so this direction was the potential. If we just draw out the potential as some contour lines, the contour line is going to be very close right next to the charge, because that's this part here. And then as you go a little further away from the charge, the contour lines will get further and further apart, like that. And that's all I'm doing is just kind of drawing this out. You could imagine it as like a very sharp peak sort of sticking up out of the board. So if we take so that's the potential, and so if we want to find out where the electric field is, which is also what the force would be on a charge, that's the definition of electric field, so it's a directional thing. It says which way would a charge be pushed or pulled. So that's basically just equal to the negative of the gradient of that potential. And so what is that? That's just the steepest uphill direction of the potential. And so, but the negative of it. Okay, so the steepest uphill is going to be sort of aimed in toward the charge, but we're taking the negative of it. And so that means that there's going to be a big arrow, here. And then as you go further out, the arrows will get smaller and smaller. So they'll all point out, from the middle like that. So that's the E field. It's perpendicular to the contour lines because it's always the gradient is the steepest uphill direction. So that's just drawing out that equation that we went over last time with the current source density, or the time before. So that's what you get if you just look at if you just plot this equation out basically across all space. That's what you would get around a charge. So these are constant. So it's basically 1 over r. Okay, so that's simple enough. But we want like a dipole. So we want like something that actually has 2 parts to it. So that's a little more complicated. So now what we have is the equation for dipole, like a positive and a negative charge, or a source and a sink. And so what that's going to be the strength again over the same 4 pi conductivity business constant. But now it's going to be 1 over the distance to the first charge minus 1 over the distance to the second charge. So what does that look like? So that's a more complicated. So if we plot out that equation in 2D, you get a little bit more of a mess. So let's just look at what that one looks like. So I'll make plenty of space. So here's a positive charge, and here's a negative charge. Or you could sort of alternatively think of it as a source and a sink. So you might, when you first think of that, like how could a charge be a sink or a source? A source and a sink is a dynamic thing. But remember, we're in the statics case where things are sort of going slow enough that we don't have to worry. So you can sort of think of a source and a sink as basically just a static charge, and then look at which way the current would go given the distribution of the field around those charges. So the first thing we have to do is plot the potential, and so there's going to be a 0 line right here in between the two. And then we're going to have that same kind of thing going on, but we have to take the other charge into account. And so what do you get? So basically what you get is a more complicated thing. So it looks something like this. So it starts to splay out quite rapidly, like that. And it sort of goes here, and then so something like that. So, and then there's going to be the same thing around this guy. So here's the same thing going around this guy. So what I'm plotting is the potential again. So this guy, let's just make sure we have, so this guy is the potential. So that's just a number. And this guy, this guy is the E field. That's a vector, the gradient of the potential. So I'm plotting the potential again here, which is a little more complicated. And you could probably recognize this. It looks like something like you might have around something like a magnet in iron filings. It might make a picture that looks a little bit like this. Okay, so now we have to take the gradient of that, because that's the potential. So that's the potential. And so now we need to take the gradient of it. And so when we take the gradient of it, what do we get? So we first get something going this way. The negative of the gradient of it. And then if you look at these, so we always have to be perpendicular to these lines. So there's a lot of constraints here. So then there's going to be, something that sort of comes along in this direction. And then it sort of, splays out. Sorry, didn't do my right angles correctly. So now we're going to have something that's going like this. So you can see how it's all perpendicular to the other contours if I had drawn it correctly. And here's another one sort of going out this way. So it's quite a complicated mess right in the middle here. And then as you get over here, it's just going straight out, just like it was before. And same way, it's going straight in here, sorry. So I'm drawing all the E vectors. And so there'll be, those E vectors will kind of come out like that. Yeah. Oops, that one's supposed to be a little further down. Okay, so they're all perpendicular to the contour lines there. Okay, so each one of these, there'll be the vectors. I'm just drawing the lines that the vectors are along. Okay, so that looks like a horrible mess. So how can we escape that? So the way we escape that is we make an approximation, which is what we're going to do for our forward solution. We make an approximation that we are kind of a long distance away relative to the distance between these two guys. So the distance between these two guys is a vector. Maybe, just get it in the right place. Okay, so this vector here is called D. It's not there's an E vector pointing in that, a couple E vectors pointing in that direction, but that's not the E vector. That's the distance, just the vector that is the distance between the two charges. I've drawn it in a different color. And again, what we're sort of thinking of this as, we're thinking of this as something like, like a cell here. Say we had a cell here, pyramidal cell, and some current went in this direction and came out here. That's our model of our dipole. So you've got current disappearing here, which is like a negative charge, and then current is erupting. The divergence is positive over here. That's like a positive charge. Okay, so how can we sort of deal with, that just looks like a horrible mathematical mess in there, so how do we deal with that? So one way to make it simpler is to make an approximation. So make an approximation that just deals with the situation when you're pretty far away. So how far away? About like 3 or 4 times farther away from the center of this dipole. So if we take like 1, 2, 3, 4. So say we're measuring from a point down here. So that's our measuring point. So if we go from the center of this guy down to our measuring point, that's going to be our R vector. So that's now these guys aren't vectors. These guys are just distances. So let me just go back to this. This is just distance. This is distance to charge 1. This to 2. Okay, so those are just the distances. But this guy's a vector now. And so when we do this approximation, several things are happening. So you know, what are several things? So we have to consider, you know, the measuring point, and the dipole orientation. So the dipole orientation was just kind of implicit here. There was no vector that sort of indicated which way the vector that goes between the two charges is. So we've added that vector that goes between the two charges, and we've added another vector which is the vector where we're measuring, and we're on top of that making the approximation that we're about 3 to 4 times d, the length of d. So what does that mean? That means like we're 3 to 4 times the distance between the positive and the negative charge, so we don't have to deal with the complicated mess in here. So that's an approximation, and that approximation gives us our basic forward solution. So before I say what it is, you might notice like there's no end in sight for the brain. We've just drawn a forward solution for a universe filled up with a brain. So imagine the simple case where the brain is infinitely large and you've got some pyramidal cell in it, and it's this effectively sort of, you know, causing current to flow because of this you know, source and sink here. And then we want to calculate what the potential is at all different points inside this infinitely large brain. Now you might think at first that's a terrible approximation to a brain, but it turns out this is the biggest factor, and what we do is we eventually just do some corrections for the fact that the brain isn't infinite. So it's important to sort of realize this one is like this you know, forward solution equation is actually explains most of the strength of the potential that you'll measure here, or the strength of the magnetic field that you measure outside the head. So this is only approximately, because this is the 3 to 4 business, you know, the 3 to 4 times business. So it's only approximate. But if you're about that far away, then you get an inverse square. So remember, this one is actually just an inverse. It's just 1 over r. So the strength just depends on basically the distance between the measuring point and the charge. Whereas in this case, this equation, it's an inverse square, and that comes from sort of the interaction between these two charges. And so our basic forward solution equation, which forward solution meaning for some sources calculate what the potential in the magnetic field is, for the potential is just 4 pi times conductivity again. But now we've got a dipole vector that tells us like what's the spacing between the source and the sink, and then we have another measuring point vector. And so here's what the equation is. It's the dot product of the measuring point vector and the distance between the dipoles, the orientation of the dipole vector, divided by the cube of the length of the r vector. So this symbol just means take the length of this vector and then cube it. But we've got it in the in the numerator too. Now remember, you could always rewrite. We could rewrite the dot product as we take the length of the d vector and multiply it by the length of the r vector, and then multiply by the cosine of the angle, between them. So let's do it for this one. So this one. So remember what the dot product does. If the vectors are in a very similar direction, the dot product that's where it's the biggest. If they're perpendicular to each other, it's 0. If they're in opposite direction, it's a big negative number. So these are almost in the opposite direction. So the dot product between this d and this r should be negative, and it's going to depend on the cosine of the angle, of this angle between this guy and this guy. So that's the electric forward solution. So it's an inverse square. And so why is it an inverse square? Because we've got r up in the top as well, and so it divides out one of the r's. So it's something over this distance squared. So this guy is a inverse square. So this guy is just inverse. 1 over r. This guy is inverse square. So that's 1 over r squared. And that also explains, for instance, why it's hard to record deep sources. Because when you try to record a deep source, as the distance gets bigger, the strength of the source on the scalp goes down as the inverse square. So it's going to go down much more rapidly. So if I'm right near the surface, I'll have like a nice big number. But as I go, and so what does the inverse square look like if you plot it here? Well, it's going to fall off much quicker like that. So what that means is if you're sort of near if your source is near the electrode, and then you just go down just a little bit, the source will drop way off. If you go down sort of toward the middle of the head, it'll just be virtually nothing. And so that basic property of the forward solution, the fact that the sources fall off as a function of the inverse square of the distance between your measuring point and the source, that's a very important feature of the forward solution. And that's what makes it hard to record deeper sources. So that's the electric. So this is the EEG forward solution. But then we need the MEG forward solution too. So the MEG forward solution looks virtually identical. So the MEG forward solution, except it's a little more complicated because it's a vector. So it's actually got 3 numbers, because the potential that you measure coming out of the scalp, that's just a number, it's not a vector. But the magnetic field that you measure at some point on the scalp is actually an arrow. It's pointing in some particular, it could point anywhere around 360 degrees, or like a whole sphere. It could basically point anywhere in the direction of a sphere. So that one is going to be, it's going to be basically perpendicular to this, this thing. You can sort of think of it as perpendicular to the currents, or to the orientation of the vector between the positive and the negative charge. Now that guy is going to have the permeability. That's the divided by 4 pi. The permeability is kind of in the numerator versus down here, the conductivity in the denominator. And then it's virtually the same equation, which is just the source strength. So this is the strength. Source strength, except the cross product with R. and then again divided by, it's another inverse, the MEG has the same sort of inverse square business going on, so it's the cube of this length of this vector. But since that vector is in the numerator, and remember you can change this into, you can change this into the length of the dot, the length of the cross product is going to be equal to, let's pull that in a little bit, times, it's going to be equal to the length of those two vectors times the sine of the angle between them. That just gives you, but then the direction is perpendicular. Remember that this guy is just a number, and so this just gives us the number. So this guy is a number. This guy just gives us the length of the vector, but it's going to be perpendicular to these two vectors because it's a vector. So this guy is inverse square. This guy is also inverse square. And so that's going to basically be our MEG forward solution. So this one's sometimes called the Biot-Savart law. You might see it, Savart law. But this is our MEG forward solution. Now, you might be sort of a little disturbed by how come you got this guy's a three-dimensional vector, the magnetic field. Most MEG detectors only detect one or two components of the vector. So you could just detect the component of the magnetic field vector that's coming outward from the head. So some detectors are like that. They just detect whatever the component of the magnetic field going this way, and they ignore any components of the magnetic field that are going in different directions, sort of parallel to the head. But there are other MEG detectors that detect just the component that's going this way, and they ignore the component that's going out, and they ignore the component that's going this way. So they just detect this component, and then you could have another one that just detects this component and ignores that one and ignores that one. So it's a little more complicated because this thing is an actual vector, whereas this is like scalp potential. Scalp potential, and this guy is MEG squid. That's what they call the detectors that detect these weak magnetic fields. And there's different kinds that you could just measure, perpendicular to the head or parallel to the head. Okay, so that's our forward solution. In the infinite brane case, so the brane extends throughout the entire universe. So that's not very practical. So how can you sort of make it more practical? So basically we just have to add some corrections. At first it sort of seems impossibly more complicated, but it turns out we just have to add some corrections, a whole matrix of corrections. And this gets a little hairy, but there's a lot of software that's been written to do this. And so it's possible to do it just for a sphere because the head's sort of similar to a sphere. That's one way. So we could do it. We can actually have analytical equations for sphere head. And that's not too bad, actually. I remember back in the day we were going through the department trying to find the person that had the most perfectly spherically shaped head. Generally, Asians tend to have much rounder heads than Europeans will have, and Africans will have sort of elongated heads front to back, whereas Asians will have heads that are more round. So we were looking for the best, most spherical head, perfect spherical head. But obviously people have all different shapes, and the skull varies in thickness, and so what you can do One way of doing it is something called of making the correction for a non-infinite head. It's called a boundary element method. And what that does is you have, the brain cavity here. So here's the brain. And then we have another compartment that is basically the skull. And then we have another compartment that's the skin. So here's the skin. Usually they just sort of cut it off at the neck. Okay, so the idea here is that we make a model of basically the same kind of model that we were talking about with the cortical surface model. So we make a model of the brain, and then we just assume that the conductivity inside here is brain. It's all the same, no difference. And then we have another one here for the skull. And so there's a big difference between the brain and the skull. Generally, the skull is conventionally, also from experiments with dead heads, the skull is 1/80th the conductivity of brain. So that means that it's much easier for the current to get through the brain than it is through the skull. But for the purpose of this kind of model, we just assume that the shape of these compartments can vary. So each one of these is a surface, a tessellated surface with triangles on it. But we just assume that, and then we have the conductivity of the skin. So it turns out, you might wonder, why do you bother with the skin since the skull is so much more important? Well, it turns out if you have an electrode up here, it's sitting on top of the skin. So it turns out a bump in the skin that you didn't account for is a bigger effect than a change in the thickness of the skull, even though the skull has, 1/80th of the conductivity. And the reason for that is because the electrode's right on the skin. So it turns out you actually have to model the skin relatively well in order to make this forward solution. And what does it amount to? It just amounts to a giant matrix of correction factors that essentially have on one dimension of the matrix as many numbers as you have points in all these compartments. So it's a giant number. It's tens of thousands of numbers. But it's well worked out. And so the assumption is that you assume that, same conductivity in each compartment. Now, it's possible to actually go completely crazy and divide the whole brain up into tiny little chunks, so that you actually instead of boundary element, you could have what's called a finite element. And that would be you take the whole brain and skull, etc., and then just divide the whole thing up into a million little cubes. Now, that's obviously computationally more expensive, but the other problem with it is you don't know what numbers to stick in there. Because, the skull has little sutures in it. Sometimes current can get through the sutures. You have to deal with the nose. It's just impossibly complicated. And we don't have any good numbers to stick in there. Whereas here we just have to put, the conductivity of the brain, conductivity of the skull, conductivity of the skin. It's not straightforward to try to measure all those numbers that would be required to make a model that actually had potentially different conductivities for different parts of the brain or different parts of the skull. So most of the time, this is a good one. This is, allows you to sort of control for the shape of the skull, Pretty good. And you can do the same thing for MEG. So for MEG, you only have to bother with this surface. So MEG is just one. EEG, you need to include all three surfaces. And so why can you sort of like not bother with the other surfaces for MEG? Well, the current doesn't really go through the skull. And so almost all of the magnetic fields are generated by current that's flowing around inside the head, so we don't have to bother about the total amount of current that actually goes through the skull is so low, the magnetic fields generated from that are almost nothing. And so we can just basically just deal with the brain. So it turns out you've got more dimensions to the magnetic field one, but it's actually an easier forward solution because it only really depends on current flowing around inside the brain. Okay, so in the last minute or two, we have to, so this looks kind of a mess. There's squares and stuff like that in there. And one of the critical things about the forward solution is that the forward solution is linear if we assume that the dipoles and the recording sites are not moving. And so this critically simplifies our approach to it. And so let me just say, what does it mean for the forward solution to be linear? So basically, so the forward solution, because then we can just reduce it to a matrix, just a simple matrix multiplication, like AX equals B. So we have so the forward solution, we can just turn the forward solution into just a simple matrix. So the forward solution is linear if the following thing. So we have basically fixed source dipoles and fixed recording locations. So as long as we just here's our electrode is right here, and we're going to go through the brain and say, so here's a little chunk of the brain, and we could say like, okay, we'll divide it up into a bunch of little chunks, and then we'll say, at each chunk you can have like a dipole, pointing up or down. It could go down, but it has to be sort of parallel to the surface, perpendicular to the surface. So these are all our possible sources. Possible sources. Those are D's. These guys. So they're in a particular position, relative to where we're recording them. And they're in a particular orientation. So they're fixed. And then we've got the recording sites. And here's the recording site, and that recording site is fixed. So if that's the case, then we're linear. But why do we care? Like, what's great about linear? So what's great about linear is that if we calculate, say we've got a source over here, and we calculate the forward solution from that single source to all these points, where that's where our electrodes are. And so we do that calculation, forward solution, using the equations that I erased that were over here, and then modified by the boundary element. And we get something, say for the EEG, we get something like that. So that's the potential from a current dipole at this location. And so then we now measure another source, and that source, looks like this. Here's the forward solution of that source. So this guy is, source, and this is the forward source. So source 1, source 2, forward 2, forward 1. So if things are linear, then what we can do is we can predict what we would get if both were on. So here's a case where both were on. So we turn on this one and this one at the same time. So we can basically predict what we would get without having to solve this forward solution. That's the critical thing, why it's great that it's linear. So what that means is that all we have to do is just take this forward solution and add it to that forward solution. And so we would basically get something like this, and then it would be a little bit up in here, and then it would go up again and go down like that. So that's forward, 1 plus 2. So here's, source 1 and source 2. So that means they don't interact with each other at all. So what does that mean? That means all we've got to do is, for a given electrode, we can reduce the problem to, like, say, here's a given electrode. All we have to do is basically, here, let me make another one last picture. Okay, so one last picture. So for a given source, say like this guy, there's a whole bunch of recording sites. So here's all the recording sites. And so what we do is, for a given source, we just calculate the forward solution for each of these guys once. So we calculate all those forward solutions. So, these are like forward n. And then we're done. And then we just do the same thing for the next source. So here's another source over here, and then we just calculate the forward solution for all these guys. And so we don't have to deal with any kind of combination because it's linear. That's the linear beauty of the linear part. So this means that once we've done this, et cetera, for all the different sources, we just have a giant table, and it just says how each single source relates to all the sensors, and then we're done. Then we can predict any possible combination of turning on sources at different amounts. So we can turn on this, any arbitrary distribution of sources. We can calculate with our linear forward solution. We can calculate what the sensors distribution we're going to observe. So that's why it's so great to be linear. And it's also easier to do a linear inverse. So there's other ways of doing this that are nonlinear, but this, if you have these fixed sources and fixed recording locations, you only have to do this complicated forward solution, with these arbitrary shaped skulls once. You just do that once for each source and all the possible sensor locations, then you're done. And then you can predict any arbitrary distribution of sources, strengths, what you're going to get, because it's linear. Okay, so I used up every last drop. So let's stop there, David, and I'll take some questions.
For dilution, are we linear for EEG? Are the conditions always satisfied for EEG? Or
okay, so yes, it's always linear, assuming that we got a fixed dipole. An example where